Last time we were introducing Hermitian operators. A Hermitian operator is one such that if I have an operator M, it's equal to its Hermitian conjugate. And these are the kinds of operators that you operate with almost all the time in quantum mechanics, because those are the operators that produce real eigenvalues, in other words, real results, or predict real results. With that in mind, we should talk about some of the nice properties that Hermitian operators have. So one of the things that we can talk about first is the eigenvalues of a Hermitian operator are real. So you get a real answer. And we can prove that very simply. Suppose L is an Hermitian operator. And let's apply it to some eigenvector lambda. And let's say it gives us some eigenvalue lambda, ket lambda. Also, let's look at the other side of it, lambda, where I apply L conjugate to bra lambda. And that's going to give me lambda. And of course, that will give me a complex conjugate of my eigenvalue. We'll call it lambda star. But if L is Hermitian, then L is equal to L dagger. And what that means then is that lambda L is equal to lambda applied to, L dagger applied to bra lambda as well. So what I can do is I can also say that L lambda is equal to lambda times ket lambda. That being the case, if I multiply the first expression by ket lambda and the second expression by bra lambda, notice what I get. I get lambda L lambda is equal to lambda times bra lambda ket lambda, and I get lambda L hat lambda is equal to lambda star. Lambda, lambda. Notice two things equal the same things or equal to each other. That means, of course, that lambda must be equal to lambda star, which is telling me that the eigenvalues are all real. Let's talk about a couple of fundamental theorems that are associated with this. First, eigenvectors of an Hermitian operator form a complete set. Any vector the operator can generate can be expanded as a sum of its eigenvectors. Two, if lambda 1 and lambda 2 are two unequal eigenvalues of a Hermitian operator, the corresponding eigenvectors are orthogonal. In other words, then lambda 1, lambda 2, 0. Both of these are important properties. 3, even if the two eigenvalues are equal, we can choose the corresponding eigenvectors to be orthogonal. Degeneracy is when two different eigenvectors have the same eigenvalues. So in summary, the eigenvectors of an Hermitian operator form an orthonormal basis. Can we prove that? Yeah, let's try that over here. So let's use L as our Hermitian operator. Apply to ket lambda 1, eigenvector lambda 1 equals lambda 1. L applied to lambda 2 is equal to lambda 2 times eigenvector lambda 2. Now, since L is Hermitian, let's flip the first equation. So I can write lambda 1 raw L is equal to lambda 1 times bra lambda 1. And by the same token, I can do L lambda 2 is equal to lambda 2 lambda 2. Put them together. Now watch what happens. Let's do the inner product of lambda 2 with the first equation, and let's do it with lambda 1 for the second equation. So we'll get lambda 1 times L lambda 2 is equal to lambda 1 lambda 2. And lambda 1 L lambda 2 is equal to lambda 2 lambda 1 lambda 2. Now let's subtract. We'll get lambda 1 minus lambda 2 times lambda 1 lambda 2 is equal to 0. So if lambda 1 is not equal to lambda 2, we know that lambda 1 lambda 2 in the brackets will also equal 0. And thus, the eigenvectors, of course, are orthogonal. Suppose L operates on lambda 1 ket. We write that as lambda 1 ket. And L operating on lambda 2 ket is equal to, we'll call it lambda, let's just call it lambda. So suppose they have the same eigenvalue lambda. Any linear combination of the eigenvectors is also an eigenvector with the same eigenvalue. So suppose A is equal to alpha lambda 1 plus beta lambda 2. L applied to A would be equal to alpha L lambda 1 plus beta L lambda 2. And L applied to A then would be equal to lambda times alpha 1 lambda 1 plus beta 1, plus beta lambda 2, which of course is equal to lambda times A. So it works. There's a procedure that is kind of interesting to go over called the Gram-Schmidt procedure. And what we can do is, sometimes we encounter a set of linearly independent eigenvectors that don't form an orthonormal set. Degenerate states in the system are known for this. We can always use the linearly independent vectors you have created in an orthonormal set in the same space. Let's show how we can do this.
15 minutes.
This is called the Gram Schmidt procedure. So suppose I have the following situation. I have a vector v1 and another vector v2. What we want to do is construct from this orthonormal vectors, we'll call them v1 hat and v2 hat, from this configuration. So step one, we're going to take v1 and divide it by its own length to get a unit vector parallel to v1. So I'm going to take v1 vector, divide by its length, and that's going to give me v1 unit vector. So that would be something like this. It's the same direction as v1. It has unit length, and we'll call that v1 hat. Let's project v2 onto the direction of v1 by forming v2 inner product with v1 and multiply by v1 hat. And now we'll subtract. Take vector v2, subtract v2, v1 along the v1 hat direction, and we'll call that v2 perpendicular. v2 perpendicular is going to be this vector right here. v2 perpendicular. Okay? And then finally, let's divide v2 perpendicular by its length to get v2 hat. And of course, that will give us a unit vector in the perpendicular direction. As you can see, v1 hat and v2 hat are orthogonal to one another by that process. That's a pretty nice trick to learn. So you can take any two vectors, and by using the Gram-Schmidt procedure, you can turn them into orthogonal basis vectors. we've reached a point in the course where we can talk about some of the fundamental principles of quantum mechanics. And this would be a good place to start. So, principles of quantum mechanics. First one. The observable or measurable quantities of quantum mechanics are represented by linear operators which are Hermitian. So anything that we expect to observe has got to be represented by an Hermitian operator, because of course if we're going to observe it, it's going to yield real eigenvalues. Which brings us to principle 2. If the system is an eigenstate lambda sub I, the result of the measurement has got to be guaranteed to be eigenvalue lambda sub I. 3, if I have distinguishable states are represented by orthogonal vectors. So the eigenvectors have to be orthogonal. 4, if A is a state vector of the system and we measure using the operator L, the probability to observe eigenvalue lambda sub I should be equal to the probability of observing eigenvalue lambda sub I would be equal to A lambda sub I A. Let's see if we can put some of these principles into practice. To do this, let's bring back our old friend, the spin operators. We want to write down our spin operators as 2 by 2 matrices. Let's start with sigma sub z. It has definite unambiguous values for states u and d, up and down. In state u, we know that sigma sub z is equal to +1. In state d, sigma sub z is equal to -1. That's the result that we get. So let's go back to our principles of quantum mechanics and apply it to spin. Each component of sigma is represented by a linear operator. Whether it's sigma z, sigma x, sigma y, all of them are linear operators. Now we can put hats on them if we want. We haven't been using hats for the spin operators, but we could. Secondly, the eigenvectors of sigma z are, as we said, u and d, eigenvalue +1 and -1 respectively. So we can say that sigma z applied to u is equal to plus u, sigma z applied to d is equal to -1 times d. 3, u and d are of course orthogonal to each other, so inner product of u and d of course is 0. We take these principles together, what do we get? If I wanted to figure out what my operator sigma sub z was equal to, what does it look like in matrix form? let's do it this way. We know, let's put it in components. We'll call this sigma z 1, 1, sigma z 2, 1, sigma z 1, 2, sigma z 2, 2. If I multiply by eigenvector u 1, 0, I should get eigenvalue 1 times 1, 0. By the same token, if I take that same operator, sigma z 1, 1, sigma z 2, 1, sigma z 1, 2, sigma z 2, 2, multiply by eigenvector d, I get minus 0, 1, right? Because the eigenvalue of d is minus 1. So, how can we make, so it's got to be that both of those two have to result if I apply my sigma z operator to ket u or ket d. The only way for that to work is if operator sigma z is the matrix 0, 1, 0, 0, minus 1. That's the only one where if I multiplied ket 1, 0, I would get 1, 0, and if I multiplied ket 0, 1, I would get minus 0, 1. Multiply it all out and solve it simultaneously if I wanted to, but I don't want to right now. Let's do the same thing for sigma x. Eigenvectors are R and L, such that sigma x times R is equal to R. Sigma x applied to L is minus L. But also we know that R and L are linear superpositions of U and D. Remember we had written R ket as 1 over square root 2 U plus 1 over square root 2 D, and L is 1 over square root 2U minus 1 over square root 2D. So I could write my ket R as 1 over square root 2, 1 over square root 2. My ket L as 1 over square root 2 minus 1 over square root 2. And my matrix multiplication would look like the following. It would be sigma x, 1, 1, sigma x, 2, 1, sigma x, 3, 1, 2, 1, 2, and sigma x, 2, 2, multiplied by 1 over square root 2, 1 over square root 2, has to equal 1 over square root 2, 1 over square root 2. Furthermore, so that's for the R case. For the L case, it's got to be that sigma x x, I'm sorry, sigma x 1, 1, sigma x 1, 2, 1, sigma x 1, 2, 1, sigma x 2, 2, multiplying 1 over square root 2 times minus 1 over square root 2 must be equal to minus 1 over square root 2, 1 over square root 2. The only way to have consistency for these two equations would be if sigma x is going to be 0, 1, 1, 0. We can do the same operation for sigma sub y, and what we will get for sigma sub y, if I do the same operation, will be that it looks like 0 minus I, 0. You may notice these may look familiar to you. These are the Pauli spin matrices. And we will talk about this a little bit further in our next lecture.